Good morning, everybody. Thank you, Christina, for the introduction. In my presentation, I would like to highlight some of our preoccupations. We present here an integrated system for advanced structural analysis and seismic performance evaluation of 3D frameworks with rigid or flexible connections. My presentation is divided in two parts. In the first one, I will make some presentations of the key elements of the mathematical formulation of the numerical procedures developed for inelastic analysis of cross-sections and also for nonlinear analysis of the wall structure, three-dimensional frameworks. And in the second part, I will present some movies with the computer programs developed. So, the need for accurate yet computational efficient tools for the nonlinear analysis of 3D frame structures forms the main motivation behind of our research work. Reliable nonlinear analysis tools are, for instance, essential in performance-based earthquake engineering and advanced analysis methodologies that involves accurate predictions of inelastic limit states up or beyond to structural collapse. For instance, in the advanced analysis procedure, accurate predictions of the nonlinear inelastic analysis of frameworks represents the key element, and such analysis procedure can directly assess the strength and stability of the overall structural system. The separate member capacity checks are not required. In this respect, a large deflection distributed plasticity analysis that includes the spread of plasticity, residual stresses, initial geometric imperfections, and any other second-order behavioral effects would certainly be suitable to be classified as advanced inelastic analysis, in which checking of beam-column interactions is not required. Reliable nonlinear analysis tools are also essential in the performance-based earthquake engineering. Accurate predictions of the ultimate limit states are essential to perform the pushover analysis, for instance, to compute the capacity curve for seismic performance evaluations of frameworks. The nonlinear inelastic static analysis procedures developed here uses the accuracy of the fiber finite element approach for inelastic frame analysis and addresses its efficiency and modeling shortcomings through the use of only one element to model each physical member of the frame. This is an essential requirement to approach real large spatial frame structures, combining modeling benefits, computational efficiency, and reasonable accuracy. The following assumptions are adopted in the formulation of analytical model. Plane sections remain plane but not necessarily normal to the deformate axis. Torsional buckling do not occur. Small strain but arbitrarily large displacement and rotations are considered. The connections could be semi-rigid, and this node is of zero length. And the joints can be considered with finite dimensions also. And the proposed approach is based on the most refined type of second-order inelastic analysis. A distributed plasticity model is involved, where elastoplastic behavior is modeled, accounting for spread of plasticity effects and in sections and along the element length. Currently, it's available several methods. One of the most used method is based on the use finite element methods, and this method required to divide the member in several small elements, and for this reason is not user-friendly for practical applications. These methods ignore many important characteristics and requirements for practical design, consistency between the linear and nonlinear models due to the need to use several elements per member to model the nonlinear effects, which enhances in this way the computational effort. The proposed element is developed in the framework of the flexibility-based approach. This element is more accurate than the displacement-based elements because internal work is derived from an assumed force distribution function that relates the internal forces along the member length to the member end forces that allows to use only one element per member to model the inelastic behavior. A sketch of the three-dimensional beam column element with 12 degrees of freedom is presented on this slide on the left side. The already mentioned assumptions allow the formulation details to be considered on two distinct levels, namely the cross-sectional level and the member longitudinal axis level. Thus, the nonlinear response of a beam column element can be computed as a weighted sum of the response of a discrete number of cross-sections that are located at the numerical integration scheme points. The cross-section stiffness may be modeled by explicit integration of stresses and strains over the cross-section area. In this case, we call the procedure micromodel, or to calibrated parametric equations that represent force generalized strain curvature response. We call the procedure as macro model. Gradual classification through the cross-section subjected to combined action of axial force and biaxial bending moments is described through basic equilibrium, compatibility, and material nonlinear constitutive equations. In this way, the states of strain, stresses, yield stress, are monitored explicitly during each step of the analysis. The arbitrary cross-sectional shape and the effect of material imperfections such as residual stresses, various cross-sectional shapes, and any other factors are accurately included in the analysis. One of the key issues in developing of such procedure represents the high accuracy and computational efficiency evaluation of elastoplastic behavior of cross-sections subjected to axial force and biaxial bending moments. Therefore, our research program has paid very careful attention to inelastic modeling of the cross-sections, developing advanced procedures for moment curvature analysis, ultimate strength analysis to draw the interaction diagrams, and automatically design procedures. Considering the cross-section subjected to the action of external bending moments about each global axis and axial force, as shown in this figure, and under above assumptions, the resultant strain distribution corresponding to the curvatures about global axis and the axial strain can be expressed in a linear form throughout the cross-section. This implies a perfect bond between the steel and concrete components of composite concrete steel cross-sections. The basic equilibrium equations, of equilibrium for the axial load and the biaxial bending moments are given in terms of the stress resultants, and the deformations field is assumed linear, and we can consider the equilibrium is expressed considering three equations for axial force and bending moments. And we can consider also complex stress-strain relationship for concrete and steel, and also arbitrary shape of the cross-sections can be accounted for. We have developed three numerical procedures in order to highlight the inelastic behavior of cross-sections. One of the most comprehensive procedure called here moment curvature analysis. We consider the cross-section subjected to biaxial bending moments and axial forces. The equilibrium between internal forces and external forces is resolved applying a numerical method, for instance, Newton-Raphson. And solving these system equations, we obtained parameters that define the deformations to the cross-sections, axial deformations, and curvatures. And in this way, we can determine for a given external forces the deformations in any point of the cross-sections. If the moment curvature diagram represents the concern, it's applied a more sophisticated numerical algorithm such as arc length method. And in this way, we have a clear picture with the inelastic behavior of the cross-section. The tangent stiffness matrix for the cross-sections relates, small changes, the deformations to small changes in the action sustained. The incremental relationship between incremental efforts and incremental deformations can be expressed as in the equations, in the matrix equations. And the tangent rigidity for major and minor axis bending are defined by solving the incremental constitutive equations and imposing the condition of constant axial load and bending moment about each principal axis of the cross-section. And in this way, we can define the tangent flexural rigidities about each axis of the cross-section, each principal axis of the cross-sections. These tangent flexural rigidities are used in the nonlinear analysis of frameworks. We can determine the stiffness matrix of the beam column element, considering the element with rigidities, with variable rigidities along the element length in function of the distribution of the efforts. Another numerical procedure has been developed to determine directly the plastic interaction diagrams. We can determine the plastic surfaces by drawing the vertical interaction diagrams or horizontal interaction diagrams. In this respect, an incremental iterative procedure based on arc length approach has been developed. At ultimate strain capacity, the equilibrium is satisfied when the external forces are equal to the internal ones, and in the most compressed or tension point, the ultimate strain is attained. And under the above assumptions, the problem of the ultimate strength analysis of composite, concrete steel cross-sections can be formulated as, given a strain distribution corresponding to a failure condition, find the ultimate resistances, axial force and bending moments about each principal axis, so as to fulfill the basic equations of equilibrium. And one of the following linear constraints you can see on this picture is accomplished. In this picture, I have detailed the procedure to determine the vertical interaction diagrams. For instance, for a given axial force and for a ratio between bending moments, we can draw automatically and directly the interaction diagram. Here are presented some key elements of the procedure. Basically, we have to resolve a system of equations with three couplet equations, imposing the constraint given by imposing the failure of the cross-section in a point, in the most compressed point or most tensional point, the ultimate strain is attained. The system of equations becomes the three couplet equations becomes two couplet equations, and these equations are solved applying an arc length procedure to and in this way we can draw the complete diagram varying the axial force with a parameter. Here it's presented the graphical. Here we have the graphical representation of the procedure, and in the left side we have the representation in the moment ultimate curvature space, and in the right side we have the interaction diagram. We can observe clearly on these representations that the peak moment where the tangent stiffness matrix of the cross sections becomes singular. This point corresponding to a balance point on the axial force bending moment space. And consideration of the arc length procedures, which can traverse the points beyond the peak points, where the stiffness matrix becomes negative definite, is essential. So that arc length procedure is essential to, is a key element of this procedure. Also, another procedure, numerical procedure, has been developed to automatically design of the arbitrary cross-sections, reinforced concrete or composite steel concrete. The aim of this procedure is to determine directly the total reinforcement area, considering known the external efforts for a given axial force and given bending moments. Automatically is determined the total reinforcement area. One of the most important aspects of inelastic evaluation of cross-sections represents the procedure for integration over the cross-section, the tensions, deformations, and so on. Most existing methods for the analysis of cross-sections under axial load and biaxial bending rely on the numerical integration of stress resultants using the fiber decomposition method in the first row, or Gauss quadrature, or computer graphics. All three mentioned methods are not numerically efficient due to the large amount of informations needed to characterize the section and the high number of operations required to implement the stress integration with a lower error level. So we choose a more efficient approach, the path integral, and in this approach the double integral are transformed in a path integral. We have in this way only to monitorize only several points on the contour of the cross sections, and this method is more rapid than currently methods, and also gives more accuracy results. We can take into account also the residual stresses. Residual stresses are explicitly taken into account, considering several distributions given in norms, European or American. Also, various cross-sectional shapes we can take into account. Usually in the fiber-based finite element analysis, fillet regions of steel cross-sections are ignored. These simplifications could lead to underestimations of the rigidity and flexural strength of the wall element and structure as well. And this aspect will be underlined here in several computational examples. It is important to mention that in the literature, this aspect is usually overlooked. Consequently, the results are not always consistent with the powerful computational models developed. Another way to consider elastoplastic response is based on force-strain relationships. We developed only for steel cross-sections such an analytical relationship in order to represent adequately the partial plastification effects associated with bending and axial forces. The effect in this approach, the effect of axial forces on the plastic moments capacity of sections is considered by standard strength interaction curves. Flexibility-based method is used to formulate the distributed plasticity model of a three-frame element with 12 degrees of freedom under already mentioned assumptions. In this approach, an element is represented by several cross-sections that are located at the numerical integration scheme points. The spread of inelastic zones within an element is captured considering the variable section flexural rigidities along the member length, depending on the bending moments and axial force level, cross-sectional shape, and nonlinear constitutive relationships. The element stiffness matrix, implicitly defined by the Clapeyron relation, will be obtained by recovering the explicit expression for the element increment strain energy. Here are presented the basic relations. And here are presented some of the submatrix, flexibility submatrix. The stiffness matrix will be determined by inverting this, the flexibility matrix. In the proposed, it's important to note that in the proposed procedure, the loading that the member lateral loads and transferred to the nodes, taking into account the element nonlinear behavior, are allowed and included automatically in the analysis. This leads to a significant saving in inputting the member loads without the need to divide the member into several elements for simulation of these loads. The equivalent nodal forces will be computed in order to accommodate member lateral loads, local geometrical imperfections, and the plastic strength surface requirements. The method ensures also that the plastic bending moments is nowhere exceeded once the full plastic sections develops. The procedures, our procedure can be applied even when a plastic hinge, full plastified cross sections forms along the element length without the need to divide the member length into 2 or more segments as in the common procedures. The geometrical nonlinear effects for each element are taken into account in the present analysis in a beam-column approach by the use of inelastic stability stiffness functions and updating at each load increment the length, axial force, and the flexural rigidity about each principal axis of the element. In this way, minimize modeling and solution time. Generally, only 1 or 2 elements are needed per member. The behavior of connection element in each principal bending direction, measure, or minor axis flexibility is represented by rotational dimensionless spring attached to the member ends. We assume no coupling between different rotational degree of freedom at the connection, and the present formulation can model both major and minor axis flexibility. Using an updated Lagrangian formulation, the nonlinear geometrical effects, the global nonlinear geometrical effects, are considered updating the element forces and geometry configuration at each load increment. And the natural deformation approach in conjunction with the geometrical rigid body qualified stiffness matrix is adopted for the element force recovery, and the web plane vector approach is effectively used to update the frame element coordinates. In order to trace the equilibrium path for proportional and non-proportional plane loads, the proposed method has been implemented in a simple incremental and incrementally iterative matrix structure analysis program. The nonlinear analysis is based on advanced procedure, arc length method. Using this method, we can determine the response of the structure even in the negative domain, post-critical, highlighting the snapback and snap-through behavior. Based on the numerical analytical procedures, some of the elements presented here have been developed a computer program. This computer program can be used to analyze three-dimensional frames made by steel, reinforcing concrete, or composite steel concrete elements. And also another computer program has been developed for inelastic analysis of cross sections. Using this program, we can make an MNF analysis. We can draw the moment curvature diagram. We can determine automatically and directly plastic interaction diagrams, and also we can design the cross sections. Now, several computational examples are given here in order to validate the numerical procedures already presented. And we'll start presentation with cross-section analysis procedures. We have here a composite cross-section with asymmetrically placed steel profile. Inelastic, the model consider inelasticity for the concrete and steel. The concrete, compressed concrete is modeled using these analytical relationships, in which is evidenced the strain softening effect. The strain softening effect has a very important role in the determination of the ultimate strain capacity. In this figure are represented the moment capacity diagrams for axial force. In this example, the axial force is 3,000 kilonewtons. We can see that if we consider the strain softening effect, the descending branch of this curve, the ultimate strain capacity is reduced, and also the capacity interaction, the interaction diagrams, the moment capacity diagrams are non-convex. In the literature, all these interaction diagrams are considered convex, but if they usually consider the plateau, they don't consider the strain softening effect. And also, more of the numerical procedures developed, found in the literature, have very much difficulties to consider this effect. So the main conclusions of these computer examples is that if consider strain softening effect, the capacity curves are non-convex, and also the ultimate strain capacity is reduced. Here, the same issue is highlighting that if we increase the compression axial loads, the ultimate strain capacity is reduced, and also the non-convexity is more aggressive. Such in these diagrams, here we can see such crazy curves. Here in the vicinity of the poor compression, the solutions are not unique, and also near to this region, the capacity curves are very strange. Another computational examples is presented here for arbitrary cross-sectional shapes, also composite. The same effects we can observe. This cross-section has been analyzed trying to determine the moment curvature diagrams, and we observed that when the strain softening effect of the concrete in compression is taken into account, the moment curvature develop snapback. The response, it's very hard to determine using the traditional methods that control analysis only in deformations. Our procedures use the arc length method. The results are controlled in deformations and loads simultaneously. Another interesting result, when considered the residual stresses throughout the encased steel profile in a composite steel cross sections, the residual stresses reduces the ultimate strain capacity, and For instance, these cross-sections is analyzed considering the different levels of the compressive axial force and different distributions for the residual stresses using European distribution and American distribution. And we can see that the ultimate strain capacity is reduced with increasing the axial force. And this reduction reach even 40%. So the consideration of the residual stresses for the encased steel cross-sections is important to take into account. The same results represented in the space bending moment and in this picture is represents the variation of the flexural rigidity with the intensity of the bending moments, and the same conclusions can be underlined. Another computational example, this cross-section has been analyzed in order to determine the total reinforcement area, considering the cross-section subjected to axial force and biaxial bending moments. For these values, we obtain total reinforcement area. We assume the distribution of the reinforcement bars to be known. The unknown is the diameter of the bars. Now, the following examples are given to validate the performance of the NEFCAD computer program. Here is a portal frame. We have analyzed this frame in order to highlight the importance of the residual stresses. We can see that for pure steel, the residual stresses does not affect very much the ultimate load, the ultimate capacity, but the residual stresses have an important role on the flexibility of the frame. So the residual stresses has to be included in an advanced analysis. For instance, this frame has been analyzed considering three distributions of the residual stresses. This is European distribution, American distribution, and this without considering any residual stresses over the cross sections. We can see here it's very clear that the plastifications develops along the entire element lengths, if we consider residual stresses. Another computational example. We was very interested in considering the exact shape of the cross sections. And for instance, here we consider Hebb profile with and without considering the fillet regions. As expected, the strain capacity of the cross section is reduced, and this reduction reach 10%. And also, this effect can be evidenced at the global structural level. The ultimate load also is reduced if the fillet regions is not taken into account. Usually, in the more sophisticated programs and in the literatures, this aspect is overlooked. The cross sections are modeled in the advanced models, in the fiber element models, without taking into account the exact shape of the cross sections. Here are several computational examples for three-dimensional frames with rigid or semi-rigid joints. We compare our results with the results retrieved from literature with more demanding methods that used very fine-grained finite elements, and our method is very compatible from the point of view of the results with these sophisticated methods, and also the computational time is more reduced. For instance, for this frame has been modeled with advanced method that use fiber finite elements. The total time to obtain the response using an advanced method based on finite fiber elements was 20 hours, and in our method we obtained similar results only in 6 minutes. So all these examples are given to validate our numerical procedure. Here are represented the plastic zone distributions in different situations: rigid nodes, flexible or semi-rigid joints with linear or nonlinear behavior. We compare the results with our results given by our model with the results obtained in the most sophisticated computer program Abacus. And as can be seen on in this graph, the results agree closely. So, the main conclusions of our research are the following. Considering the inelastic response of the cross-section, the proposed approach is general, can determine both moment capacity contour and interaction diagrams, the horizontal curves and vertical interaction curves. The proposed method is fast. The diagrams are directly calculated using solving at a step just 2 coupled nonlinear equations. The proposed method is very stable. The method is not sensitive to how the origin of the reference loading axis is chosen. It is not sensitive to the strain softening exhibited by the concreting compression and to the nonlinear constitutive relationships. It is not sensitive to the initial or starting values. And very important, the proposed method reveals multiple solutions in the vicinity of poor compression. The interaction diagrams are non-convex. And also, we highlighted that the residual stresses play an important role when the compressive axial force is high. Concerning the nonlinear analysis of frameworks, we can model the nonlinear response by only one fiber beam column element to take into account the geometrically and inelastic behavior. We use only one element per member, and it is allowed to consider gradual yielding associated with biaxial bending and axial force, gradual speed of plasticity. We can model at the level macro and macro the inelastic behavior of cross sections, either using fiber take into account explicit nonlinear constitutive equations, or modeling the inelastic behavior of cross sections through analytical force-strain relationships. Also, local and global nonlinear geometrical effects can be taken into account. Nonlinear semi-rigid joints, distributed loads, and we can determine the complete nonlinear behavior, pre- and post-critical response. We can determine the snap-back and snap-through phenomenon. The future works is envisaged considering lateral torsional buckling. This effect is very important to be considered in an advanced analysis. And also for seismic performance evaluations, we implement advanced pushover methods considering the adaptive force distribution and higher modal higher modes. With my young colleagues, Dr. Alexandru Chira and Dr. Marius Buru, we started a new program. The goal of this research is to meet a need guidelines that can aid nonlinear structural analysis software developers and structural engineers in understanding the requirements for capturing member and system strength limit states via advanced nonlinear elastic analysis models developed in software that require very fine-grained modeling using fiber, shell, or volumic elements. The Abaco software package will be used in this research in order to validate the new computer methods, as well to determine its limitations. Will be selected several benchmark problems and solutions that will be used further in the calibrating process of the new developed computational procedures. This represents a real need because in the open literature, only a few benchmark frameworks can be found and are not always well documented, and the solutions are given using FEM software that use only line elements. So if I have only 2 minutes, I will show some movies in the computers. And meanwhile, if any questions you have, here is NEFCAD. You can see NEFCAD in action, topology of the structure. As in linear models, the frameworks are modeled using only one element. Here we can see a reinforced concrete frame. Explicit the inelasticity is taken account using nonlinear stress-strain relationships for concrete in compression or tension. We can consider various arbitrary cross-sectional shape, explicit distribution of the reinforcement bars, and different stress-strain relationships for concrete and steel. I will accelerate a little bit because these steps you know very well. Here is simulated seismic analysis, the loads given by the loads associated to the first mode of vibration and the gravitational loads also. The analysis is very quickly, in only 2 minutes, this structure has been analyzed, and we can see very clearly the load deflection relations response, the distribution of the plastic zones for each member, and for each member we can see very clearly the distribution of the plastic zones throughout the cross sections and also along the entire element length. Flexural rigidities about each principal axis, and so on. Deflections until the collapse. Okay. This is first program, and the second, please. See. Okay, this is a computer program SEP. Using this computer program, we can determine the moment curvature response. We can determine the plastic interaction diagrams, and we can design any cross-section. We can design the reinforcement bars in the case of reinforcing concrete or composite steel concrete cross-sections. Here is an example how to draw the vertical interaction diagram. This is composite cross-section, as you can see, and the procedure is very quickly. We can see explicitly the distributions of the plastic zones, the yielded bars, and any other important parameters. Okay, thank you.